this video, we're going to learn about autonomous first-order differential equations and how to analyze their solutions without having to solve the equation. We'll start by walking through an example to see what makes an equation autonomous, see how to find the critical points, and then construct a phase portrait. We'll also learn to classify critical points as stable, unstable, or semi-stable, and use slope fields to sketch some solution curves. Finally, we'll look at some more examples so that you can see how the analysis changes when an equation has different numbers of critical points. Let's get started. Let's look at the autonomous differential equation example, dy dt is equal to 1 minus y squared. When you're given an autonomous differential equation, there's a few things you're usually asked to find, and we'll go through these one at a time. An autonomous first-order differential equation has a first-order derivative, you usually put it on the left, equal to a function of the dependent variable. It is not a function of the independent variable, in this case, t. In the example that we're working with, this one right up here, our f of y is equal to 1 minus y squared. We're going to need that in a minute. The first thing that we want to find are the critical points and the equilibrium solution or solutions. Let's first talk about what these are. A critical point is just a point that we'll notate as c sub I, where f of y is equal to 0. And then an equilibrium solution is just the constant solution given by the equation y is equal to c sub I. Let's find the critical points for our example. In our example, f of y is equal to 1 minus y squared. And to find the critical points, you just set that equal to 0 and solve for y. So we get y squared is equal to 1, and that gives us that y is equal to plus or minus 1. That tells us that our critical points are c1 is equal to 1 and c2 is equal to minus 1. Now let's find the equilibrium solutions. Those solutions are just going to be y is equal to our first critical point, which is 1, and then y is equal to our second critical point, negative 1. Second thing that we need to do is construct the one-dimensional phase portrait. Let's start by learning about what that is. A one-dimensional phase portrait, sometimes called a phase line, includes the critical points and shows whether solutions increase or decrease between those points. Let's construct the phase line for our example. I'm going to put down again that we have f of y is equal to 1 minus y squared, and we found our critical points are 1 and negative 1. We'll take these critical points and we'll put them on our phase line. We're going to label this as 1 and this one as negative 1. Now what we need to do is determine whether solutions increase or decrease between these critical points, and we'll add that information to our phase line. There are two methods that we can use to do this. The first method is called the analytical method or the derivative test. This is definitely the easiest method, but it has a drawback because sometimes it doesn't work. With this method, we are going to check the sign of the derivative f prime at y at each critical point. If the derivative of f at a critical point is greater than 0, then the solutions are going to move away from the equilibrium solution. We usually notate this with arrows like this. One like this, and one like this, and in between those two arrows is the equilibrium solution. If the derivative is less than 0, then solutions are going to move toward the equilibrium solution, and we notate this with two arrows that move toward the equilibrium solution. And if the derivative is equal to 0, the test is inconclusive, which is why we have to have two methods. Let's understand how this works with our example. We have f of y is equal to 1 minus y squared, and then we have our 2 points. Our critical point C1 is 1, and our other critical point equal to -1. Let's take the derivative of f. So f prime at y is minus 2y. Now we substitute in each critical point. We'll first substitute in 1. That is going to give us minus 2, which is less than 0. So that tells us that our solutions are going to move toward our equilibrium solution. Let's go over here to the left and put this on our phase portrait. Here's 1, here's -1. We just tested the point 1, and we found that our solutions are moving toward the equilibrium solution. So we're going to put an arrow like this and an arrow like that. Now let's look at f prime at -1. This is going to be equal to 2, which is greater than 0, and that tells us that our solutions are going to move away from our equilibrium solution. Over here to the left, at -1, when they move away, we're going to have an arrow like this and an arrow like that. Now let's go over the second method. We wouldn't need that method for this example, but we are going to need it for other examples. This is called the graphical method. And in this method, what we're going to do is check the sign of the function f, not the derivative this time, just f. And we're not going to check it at the critical points because at the critical points it's equal to 0. So what we're going to do is we're going to check it above and below each critical point. If our function, which is equal to the derivative, that goes back to the definition of an autonomous differential equation, if that's greater than 0, then solutions are going to increase towards larger y values. And then if our function is less than 0, the solutions are going to decrease towards smaller y values. Let's see how this works for our example. We again had f of y is 1 minus y squared, and our critical points were 1 and -1. So what we have to do is check the value of our function between these 2 points. So what I'm going to do is I am going to check a point that is greater than 1. So let's check y is equal to 2. And then if we pick a point between those 2 critical points, we could check 0. And then we need a point below -1. So let's check -2. F at 2 is going to be 1 minus 4, and that is less than 0. So our solutions decrease. And we're going to indicate that with an arrow going down. Let's go over here to our phase line, and let's put that in. Our critical points are 1 and -1, and we're in this region right here above y is equal to 1. And we saw that the solutions decrease, so our arrow is going to go down. Now let's check f at 0. That is going to be 1, which is greater than 0. So our solutions are going to increase, and we'll have an up arrow. We are in this region right here, and our solutions increase. So we're going to do 2 arrows, one up here, and then one here. You always put an arrow beside each critical point. And then our last one, we're going to have to squish it in here, f at -2. This turns out to be also less than 0, so our solutions decrease, and we're going to have a down arrow. Let's go back over here to the left. We are in this region right here, and we have an arrow going down. So you can see from both of these phase portraits that they're the same. So for this problem, either method worked. Now that we know our critical points and we have our phase portrait, we are going to classify each critical point as stable, unstable, or semi-stable. Let's first learn what these definitions mean. If we have a stable critical point, nearby solutions are going to move toward the point. If we have an unstable critical point, nearby solutions are going to move away from the point. And then if a critical point is semi-stable, that one's really interesting. Nearby solutions are going to move toward the point on one side and move away from it on the other. I'll do an example here in a minute that has one of these points. Let's now classify the critical points from the example we've been working on. Let's go ahead and put our phase portrait here. We had our critical points, and then let's put in our arrows. We had arrows that looked like this. Let's first classify the critical point that's equal to 1. You can see that solutions are moving toward this point, so we can classify this point as stable. Now let's look at the point -1. Solutions are moving away from that point, so this point is classified as unstable. Now what we're going to do is put all of this together and sketch some solution curves. I drew this slope field on Desmos. It's a free graphing calculator, and it makes really nice slope fields. Let's start by drawing our equilibrium solutions. Our equilibrium solutions where y is equal to 1, that's this line right here, and then we have y is equal to -1, and that's that line right there. Now let's look at what happens in these three regions. If we have an initial condition that lies above the equilibrium solution y is equal to 1, such as this point right here, that's -2, 2, a solution curve that passes through that point is going to look like this. It's going to start up here, and then it's going to come down here, and it's going to go to that equilibrium solution. Now let's look at what happens if we have a point that passes through the origin. That solution is going to start over here on the left on this equilibrium solution. Then it's going to come up, pass through the origin, and then go to the upper equilibrium solution. Let's do one more. Let's do one over here on the right-hand side. Say we have the point 2, -2. That's this point right here. Our solution curve is going to start over here on the left on the equilibrium solution, and then come down, hit that point, and continue on down. It's really great how much information we can learn about the solution to one of these equations without even solving the equation. Let's look at two more examples, and they're a little bit different. In this first example, we have the derivative of y with respect to t is equal to y squared. The first thing that we want to do is find the critical points. So we're going to take our right-hand side, y squared, set it equal to 0, and that's going to give us the solution y is equal to 0. So we can say that our critical point c is equal to 0. I'm calling it c because there is just one of them. The second thing that we want to do is construct our phase portrait. Let's draw our line, and then we're going to put in our point y is equal to 0. Now we need to find out how the solutions behave above and below this point. Let's first try the analytical method. That's the one where we just look at the derivative. So we have f at y is equal to y squared, and our derivative f prime of y is equal to 2y, and then we plug in our critical point. So we're going to have f prime at 0, and we get 0. I'm going to put a big X there because this method won't work. It is inconclusive. So what we have to do is go to our second method, which we called our graphical method. We want to find points above and below our critical point. So I am going to check y is equal to 1, that's above, and then y is equal to -1, and that's below. So we take our function, f, and we substitute in 1. So this becomes 1 squared greater than 0. And that means our solutions above our equilibrium are going to increase. And then let's check f at -1. This is also greater than 0. So there our solutions also increase. Let's put this information over here on our phase portrait. We're going to put an up arrow in both regions. Now what we want to do in step 3 is to classify this critical point. This critical point is called semi-stable. Let's highlight that. And the reason that it's semi-stable is that above the critical point, the solution is moving away, but below the critical point, the solution is moving toward. And that's why it's called semi-stable. Let's now sketch some solution curves. Let's start by writing our equilibrium solution in red. That's going to be the line y is equal to 0. Now let's pick a point above the equilibrium solution. I'm going to pick the point -2, 1. That's this point right here. And our solution is going to start at our equilibrium, pass through here, and then go up. Now let's pick one below the equilibrium. We can pick this point here, -2, -1. And for this one, the solution is going to start way down here. It's going to go through this point and then over to our equilibrium solution. So solutions are moving away from the equilibrium solution and toward the equilibrium solution. Let's look at one more example. This example is going to have 3 critical points, and that's a little bit trickier, so I wanted to make sure to do one of these. The first thing that we want to do is find our critical points. So let's write down that f of y is y times y minus 1 times y minus 2. It's nice that it is already in factored form, so we can see by setting this equal to 0 that we're going to get the critical points C1 is equal to 2, C2 is equal to 1, and then C3 is equal to 0. Let's go ahead now and construct our phase portrait. Gonna have to make this pretty big because we have 3 critical points. We have our critical point 2, we have 1, and we have 0. Let's do the analytical method first. For that one, we have to take a derivative. So let me go ahead and let's write down our function again. And then what we're going to have to do is multiply it out so we can take the derivative without having to use the product rule. Our function is going to be y. If we multiply out the last 2 terms, we're going to get y squared minus 3y plus 2. So our function is y cubed minus 3y squared plus 2y. Now we can take the derivative. We are going to get 3y squared minus 6y plus 2. Now we can go ahead and find the sign of the derivative at each critical point. We're going to get a 12 minus 12 plus 2. We only care about the sign, so we'll just say that it's greater than 0. So that means that our solutions are going to move away from our equilibrium solution. Let's go over here to our phase portrait and let's put in the arrows. We're at 2 and our solutions are going to move away. Now let's do the same thing for 1. We're going to get 3 minus 6 plus 2. That is less than 0, so our solutions are going to move toward. Let's notate this over here on the left. We're going to have an arrow moving toward. And then lastly, let's plug in 0. This is equal to 2, which is greater than 0, so our solutions are going to move away. So we come down here to 0 and we put arrows moving away. Now I just want to show you what happens if you use the graphical method. For this one, when you have 3 points, I think it's easiest to go ahead and just draw a line. We're going to mark that Y. I think it's just easier to make it horizontal. Now we're going to put in our critical points. And what we need to do is we need to find the value of F. Let me go ahead and let's highlight that up here. Let's use this form right here. And we need to find if f is positive or negative. If we pick a point less than 0, such as -1, this is negative, and this is negative, so f is going to be negative. You then do the same thing. Maybe in here you could pick 1/2, and it turns out that f is positive, and then picking other points will give you a negative in this region and a positive in that region. When it's negative, we're going to have a down arrow, and then we'll have an up, a down, and an up. And that agrees with what we already have from the analytical method. In step 3, we need to classify our critical points. So let's go back up and let's look at our phase portrait. Let's look at our critical point 2. Solutions are moving away from the equilibrium solution y is equal to 2. So 2 is considered unstable. Let's now look at 1. Solutions are moving toward that solution. So our critical point is stable. And then let's look at 0. Solutions are moving away from this critical point. So this one is unstable. Let's just put an arrow here because I put the solutions up there. Now we are all set to draw some solution curves. Let's start by drawing in our 3 equilibrium solutions. We have y is equal to 2, we have y is equal to 1, and we have y is equal to 0. Let's first draw a solution curve in the region above all the equilibrium solutions. Let's pick the point x is -1, y is 3. Our solution is going to start on the equilibrium solution y is equal to 2. And then it's going to come up, pass through our point, and continue on up. Now let's pick a point between the equilibrium solutions 1 and 2. Let's choose x is -1, y is 1.5. So that's that point right there. We're going to start at the upper equilibrium solution, pass through that point, and go to the lower equilibrium solution. Same thing's going to happen if we pick this point right here between these two. We're going to start at the lower and go to the upper. And then we'll do one more. Let's pick a point below y is equal to 0. We can pick this point right here. We're going to start at the equilibrium solution y is equal to 0. And then we're going to go down through this point and continue on down. And that's it. You now know how to analyze autonomous first-order differential equations by finding critical points and equilibrium solutions, constructing phase portraits, classifying critical points, and using slope fields to understand the behavior of solutions. You should be all set now to work through some practice problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.